Be surprised, I'm actually paying attention a lot.
Let's go ahead, so if we were to take the determinant of minus 2 minus lambda 4, 1 minus 2 minus lambda, all right, we're going to get lambda squared, all right, what's the middle term going to be? Plus 4 lambda, thank you, all right. Again, you'll get better as you get more experience with this, doing that. What's the constant term? 4?
Or minus 4, which this is
It should be plus 4. Wait, plus 4 minus 4, so.
Plus 4 and minus 4 is?
0.
0, good. All right, so this tells us our eigenvalues are going to be lambda 1 equals 0, lambda 2 is equal to what? Minus 4. Now lambda 2 equals 0 told us what? Notice, isn't this just a constant multiple of that already? All right. And so what we have, specifically, we've got that, well, let's just do it. 4, well, let me do it this way. If I were to do the equilibrium solution, we're solving minus 2, 4, 1, minus 2, x1 equilibrium, x2 equilibrium, then, all right, equaling 0, 0. Then isn't that solution just x1 equilibrium is equal to 2x2 equilibrium?
Yes. So it's just a multiple of 2, whatever.
Okay,
So 2 and 4.
so any combination where the equilibrium, where the x value is twice the value of that, is an equilibrium. That means it's stationary, it's sitting there. Okay, so, no surprise, so if we want to do 4 lambda 1 equals 0, what is the eigenvector xc1? 2, 1. Okay, 2, 1 would be a fine one. Would be a fine one to use. All right, and let's look at 4 lambda 2 equaling minus 4. Let's see if we can get my xz2. I'll go ahead and write this down. If I put the minus 4 in here, this will give us a 2, 4, 1, and the minus 4 there, 2. Right? Right? So, give me an appropriate eigenvector for that.
Negative 2, 1?
Okay, negative 2, 1 sounds great. Okay? All right, now let's draw these particular pictures here. Erase that. Okay, so let's draw this eigenvector here. How am I going to draw that? 2 in the x1 direction. Let me go ahead and the axis again. Going to go out 2 here, 1 here. And that one's associated with lambda 1 equals 0, right? So what's the flow along that? Let me go ahead and write down here my x of t is going to be equal to c1, 2, 1, e to the 0t. What's e to the 0t?
1.
Okay? So, plus a c2 times minus 2, 1, e to the minus 4t. Okay, so along here, it does what? There's no motion, is there? There's no time dependence along this whole thing. Let me use my other pen to emphasize this. This is a line of equilibrium.
What is that?
That means you start on that point and it doesn't move, does it?
Oh.
Is it not moving, meaning an equilibrium?
Yeah.
No motion, equilibrium. All right, let's draw this other eigenvector. Where does it go? -2 here, 1 up here. So let's go ahead and draw it this direction. Okay, and that's my lambda 2 equaling -4. What's the behavior along that?
Definitely moving towards.
Everything is heading towards the equilibrium. This is where it gets a little bit tricky, is how do I complete my phase diagram? Well, the point is that we're basically only looking at one-dimensional flow. All that flow is going parallel to this particular direction. So we just draw a bunch of parallel lines here. And everything flows in the direction heading towards that line of equilibrium. Because ultimately, if you start any place in the plane, you're going to eventually decay towards that equilibrium line. And once it gets near that equilibrium line, it doesn't move. So this I would just call as a stable line of equilibrium. Yes.
If both eigenvalues are 0, do you just like not have any movement?
Repeated roots is going to be a special case. Great question, harder. People remember null spaces and higher null spaces? I asked you to review it. Not gonna review it before we get to that case. Okay, so this particular case is sort of unique. It's a degenerate case, where the chances of hitting a 0 eigenvalue is pretty small. But when you do, you're left with a line of equilibria. And this is a stable line. The other possibility would be what? That the other lambda was, instead of being negative, would be positive, and then what's going to happen? Everything's moving away from that stable line. Okay? It'd be an unstable line. Okay. So there's the values, there's the eigenvalues, eigenvectors,